is this section is exponential functions, and then after we do that, we finish this part of the class up with the rest of the material before we get into trig, is logarithms and stuff. This stuff on the first page is just stuff that I like to kind of give for students. You don't have to necessarily know all those prefixes or anything, but that's kind of a reasonable thing to look at. A lot of you are going to be engineers and stuff. Of course, you'll deal with that kind of stuff all the time, and measurements and stuff like that. So we're just going to kind of do a quick review of exponents. One thing that I kind of like about this kind of shows you how things, like in my career as a teacher, you know, when computers first started coming out and I was teaching computer programming, it was common for a computer to have kilobytes of memory. I remember I even had a 256 kilobyte expansion slot to put on a computer, and it was the size of a brick. I mean, I was all excited that I got all this stuff. So where we are now, most of your personal computers now kind of have terabytes of memory pretty much now. You'll get 1 or 2 terabytes. So it's the way things are going, okay, just I don't know how long it'll be before you're going to have your computer's going to have petabytes of memory. And it's kind of the way the computer speed goes too. You know, you've got microseconds, nanoseconds, all the way to attoseconds and so forth. So this is kind of the prefixes or powers of 10 like that. All right. What I want to do on this next page is I want to go through just kind of a quick little review of exponents. Sometimes students need this, just depends. So when you're dealing with logarithms, then it ends up being real important that you really understand exponents and understand them well. So a lot of this stuff you already know. So the first thing is I'm just going to have you write an example for a few of these things. So this one you see all the time. If you had, whoops, that's not what I meant to do. If you had a number to the first power, of course, it's just itself, okay? If you have a 0 exponent, so if you take any number to the 0, that's equal to 1. And somebody had to figure this stuff out, by the way. I mean, there was a time when people historically had no idea that a 0 exponent made any sense. One of the reasons I like to give you this diagram is it's very logical. If you look at how the powers of 10 go, it follows a nice pattern. So 10,000, 1,000, 110, I mean, it makes logical sense that 10 to the 0 would be 1. And then when you get into the negative exponents, you just start getting into fractions and so forth. Because there was a time, you know, really before Newton, in that time when people didn't really have any concept for what a negative exponent was until we started thinking about, you know, place value and this kind of thing like that. The other thing is we've already been doing this a lot, so this is quick review stuff. So if you had something like x to the second times x to the fourth, you know that what you do when you multiply variables, you add the exponents to simplify that, okay? If you ever happen to forget that, students do forget stuff like that sometimes, x squared just means x times x. X to the fourth just means x times x times x times x. So there's a total of 6 x's. What you're doing is addition really is a shortcut for counting. Okay, human beings started by counting. They didn't know anything about addition. They invented addition because they got sick of counting. All right, that's really the way that goes. So that's what you're doing is totaling things up. Okay, this one goes like this. Okay, we've done this semester. So let's just do a simple example. Say that you had x to the third to the second power. Okay, well, what you do in this case is you multiply the exponents to get x to the sixth. So you want to know the situation and how it works. The reason for this is actually real simple. You know that anytime you square a number, you're just multiplying something, that same thing out twice. What you're multiplying out twice is x to the third. So I'm just going to write that x to the third as x times x times x. Well, that's what the meaning of x to the third squared is it's 2 groups of 3. That's what multiplication is. It's multiple groups of the same number. That's a shortcut for addition, okay? So if you kind of think of it that way, that might help you understand the y part, and then hopefully that will sink in with you a little bit better, because students are kind of bad about getting those 2 rules mixed up a little bit, okay? This one you'll see from time to time. This just says if you had any expression, it doesn't matter what it is. You could have a bunch of things, x, y, z, and if that was to the fourth power, well, you know that would mean that that's being multiplied out 4 times, but ultimately you would get this result. Okay, just everything in that parenthesis is being raised to the fourth power. That's what that says when that pops up. Okay. The other thing I want to review real quick is the negative exponent idea and the subtraction property. And this is kind of how we logically figured out that negative exponents made sense, was kind of put out of this subtraction property. So what this would say, I'll give you a simple example on this. If you have x to the fifth over x to the third, you subtract exponents, so you would get x to the second. Okay, and the way I always teach this is like this, very logical. It's really all you're doing is which part of the fraction has more x's. The top has more, the top has 2 more, right? So you end up with 2 after they cancel out. So the reason for this is x to the fifth, of course, is 5x's multiplied. X to the third is 3. All you're doing is just dividing out those, and you're left with 2. Okay, that's why you subtract exponents. You're just taking off the ones that cancel anyway. Okay, all right, so that'd be the idea. Now let me ask you this, though. What if we had x to the second over x to the fifth? Okay, which part of the fraction has more x's, top or bottom? The bottom. How many more? 3, so it's 1 over x to the third. Okay, I mean, you subtract exponents. This is how we figured out what negative exponents were, by the way. So you know the answer is 1 over x to the third. It's the only thing that makes any sense. But if you subtracted the exponents, you would get x to the negative 3. So therefore, x to the negative 3 has to be 1 over x to the third. That's the way I think of it. Okay, does that make sense to you? Okay, all right. You know, the better you understand rules, the more likely you are to remember them, is my theory. Okay, so we've already worked with negative exponents a little bit. So the idea is like if you had a number or whatever, 2 to the negative 7, that's 1 over 2 to the 7th. Okay, those properties, you'll do this in calculus all the time. When you learn how to do derivatives, you've got to understand how to work with negative exponents. This one is just doing that backwards. If you had a 1 over a number to a negative power, then you simply bring that to the top like that. Okay, so those are really all of your exponent rules. And as you're working with logarithms and stuff, you'll be reviewing this stuff anyway. So if you've already got it down, that's awesome. If you need to review it, then you need to review it. Okay? All right, so what we're going to get into in this section, primarily what we'll work with today, is the graph of exponential functions. And you have to understand exponential functions in order to really understand what a logarithm is. So that's why we do this before we get into the logs. Okay, so an exponential function is going to look like this. Okay, just something like 3 to the x. Okay, the unknown is the exponent, and then the 3 is the base. Okay, and then the graphs are always going to have kind of a similar structure to it like that. This number right here has to be greater than 0. A has to be greater than 0, and it can't be 1. The reason it can't be 1 is because then you would have 1 to the x. Well, what is 1 to any power? 1. That's not exponential. If you graphed y equals 1, it's a line. So when a is 1, it becomes a line. So basically, you're going to be looking at numbers, positive numbers that are not equal to 1, that are to the x power. Okay? When you're dealing with an exponential function, the domain is always going to be all real numbers. And the idea is, if you have a number, this power, an exponent can be anything. Okay, so exponents can be any real number. There's no such thing as a number that can't be an exponent. Fractions can be irrational numbers. Pi can be an exponent. Anything can be an exponent. Okay, so the domain's always all real numbers. A lot of what we do in this section, we'll do the transformations. So your exponential piece is that a to the x right there. But this b right here would just be basically a stretch shrink factor like we learned for all the rest of the functions. Okay? So the way I'm going to approach this section is we're just going to do a graph of several transformations, and I'm mostly just going to do 2 to the x over and over again, but do little changes to it, okay, like that, okay? All right, so what we're going to do on this first one, and to understand this, you have to know the exponent properties. So we're just going to fill out this table of values. I just made these numbers up because these are good enough to illustrate what you need to know. So I'm going to start here. So we're going to do 2 to the 0, which is what? That's 1. Anything to the 0 is 1. Then we have 2 to the first is 2. Anything the first power is itself. And then we have 2 to the second is 4. Okay, then 2 to the 10th, 1,024, I think. Somebody put that in the calculator real quick. Tell me if that's right. I kind of know them up to a certain point. Is that right? Okay, all right. Okay, now we go to the negative one. So we do 2 to the negative 1. What's 2 to the negative 1? 1 over 2 to the first, right? So that's 1 over 2 to the first. So that's a half. Let's not use a decimal. Let's just use a fraction. If you do 2 to the negative 2, what would that be? 1/4. Okay, good. That's 1 over 2 to the second. So that's 1/4. If you did 2 to the negative 10, that's 1 over 2 to the 10th. So that would be 1 over 1,024. Okay, like that. Okay, so see what happens. Exponential functions have kind of a nice pattern to them. I want to show you this first of all. You'll see the pattern on this. 1, 2, 4, then it would go 8, 16, 32, so it doubles. If that was a 3, then everything would triple. If that was a 4, everything would quadruple. So that's how you can look at a table and tell that it's exponential, okay? It's always going to quadruple by that, or double or triple or whatever. Okay, so let's graph this then. So let's get the main points on here. So we got 0, 1 as a point. You want to plot the point 1, 2 and the point 2, 4, like that. 10, the reason I gave 10 is because I want you to know when you get out here, the graph is just going to infinity. So the further out you go, the bigger the graph gets. So this graph is going to do that kind of thing like that. It's going to go to infinity. What happens in the negative numbers is, okay, you got -1, -1/2, -2, -1/4. If you go way out here, that's just getting close to what number? 0. Okay, because it's just going to be 1 over a bigger and bigger and bigger number. So what you're going to have is the x-axis is going to be like a horizontal asymptote. So that's what the graph of y equals 2 to the x looks like, is like that. Okay, your horizontal asymptote would just be y equals 0. Okay, so that's how the graph of a basic exponential function goes. If it was 3 to the x, the numbers would go 1, 3, 9, 27, 81, they would triple. Okay, but it's going to have the same structure. It's going to level off at the x-axis and then just go off to infinity when you get bigger. So that's the idea. Okay, all right. Now let's do the next one. What we're going to do is just do transformations on this. So with this one, we're doing -2 to the x. What do you suspect will happen on that? It's going to reflect, exactly. See, functions are always the same. What that number right there does is that's really a -1. So what it does is it multiplies all the y values by -1. Okay, so what I did on this one, I went ahead and just took the graph we already did. We already did this table of values here. Well, all that's going to happen on this is all these y values are going to become negative. So just, fill this out real quick and then we'll graph it. And that's what would happen is everything would reflect the way we would expect it to reflect. Okay, so it goes like that. All right. So let's just plot the points, just kind of enough to get the shape. So you would have 0, -1. You would have 1, -2, and then 2, -4, and then the graph is going to go like that, and then it's still going to go towards the x-axis. It's just all these fractional values are just underneath the x-axis like that. So that's what that negative does. It impacts the y values by making an opposite. And this in the calculator, you just put -2 to the x. The horizontal asymptote still y equals 0. Okay? So you want to get in your mind kind of the way the exponential function is always going to kind of have that structure to them. Sometimes they'll be real steep. Sometimes they're a little bit slower to go to infinity like that. All right, everybody with me so far? Okay, all right. When you learn graphs, you just kind of crunch out numbers at the beginning. Then we'll kind of take the approach of doing some basic transformations is what we're going to do then, okay? All right, so on the next page, we're going to begin to look at y equals 2 to the x plus 2. And so again, what I'm doing on these problems is I'm just giving you the basic one. The basic elementary function is y equals 2 to the x. And we're just going to graph the final thing. Let me see if you guys know what would happen on this. What do you think? Yeah, how do you know? Well, it's inside the function, okay? So that is going to take everything to the left too, okay? Okay, that's if it's adding and subtracting in the exponent, that's what it's going to do. Now, what I'm going to do on this, the way to show this is just to number crunch. So I'm going to start with actually this number right here, and I'm just going to plug in to this. And this is the only way to really appreciate how this goes is just a number crunch. So that's 2 to the -2 plus 2. So that's 2 to the 0. So that's equal to 1. Okay, so you've got that. I'm going to keep doing that for everything. I'm going to do -1. I'll plug it in. That will be 2 to the -1 plus 2. That's 2 to the first. So that's equal to 2. All right, I'm going to do it a couple more times until the numbers get too big. So I'll plug in 0. So I have 2 to the 0 plus 2. That's 2 to the second. That's equal to 4. Okay, now what you want to know on this too, you want to know about the patterns. You don't have to number crunch anymore. If you've caught on, you can tell me what that's going to be. 1, 2, 4, what's that going to be? 8, 16, 32, right? Okay, I mean, you don't have to tediously do all that stuff. You're going to know that already, see. That's how exponential functions work, okay? And then this one would end up being -1/2, like that. So what I'm trying to show you on this is notice, see how everything went this way? See, the 1 went there, the 2 went there, the 4 went there. Everything went literally to the left too, okay? And we've already learned about that. The plus seems like it would make everything go to the right, but it doesn't. Everything shifts backwards this way. Okay, so that's how that goes. So let's just plot a couple of points on this then. So just do like the point -2, 1, and then do the point -1, 2, and then the point 0, 4, and then you got the point 1, 8. Like that. So that's how the graph would go, and it still is going to level off at the x-axis like that. So as you kind of compare those two graphs, you can see that that thing has switched to the left too. That's the way to understand that, is just number crunch and see how things adjust in the table. Okay, the horizontal asymptote is still y equals 0. Most of the more modern calculators, if you have like a TI-83 or something, you would have to put 2 caret x plus 2. If you have the 84, you don't have to worry about because it just superscripts that anyway. But if you have an older calculator, you do have to have that thing in parentheses like that, okay? All right, so that's kind of the idea. That's a left 2 transformation, okay? The next one, we have 2 to the x and then -3. Now that -3 is outside of the function, so what do you suspect that does? Moves it down, exactly, okay? If that was plus +3, it would go up. Okay, so you're outside the function, so that's going to go down 3, like that, okay? So all these things work exactly the same way on every single function you learn. If it's inside the function, it changes x. If it's outside, it changes y. So really all you're doing is just adding negative 3 to these. You can do this in your head. That's 1 minus 3 would be negative 2. 2 minus 3 would be negative 1. 4 minus 3 would be 1. That would, I guess, be 1,021, and so forth. Now, I'm not going to worry about the fractions because it doesn't really matter anyway. What's going to happen on this is, since you're going down 3, the horizontal asymptote is not going to be y equals 0. What's it going to be? Y equals negative 3, right? Okay. So you're going to do that, and that's all that matters, is that you get that horizontal asymptote graphed out. So what you want to do is you want to just sketch in a horizontal asymptote at y equals negative 3, and then we'll just plot, these points, and this is good enough. Okay, you got 0, negative 2, 1, negative 1, 2, 1. That's good enough. Okay, then just kind of sketch the shape, how it goes like that. So that's the same graph, but everything has been moved down 3. That's the idea. All right, any questions so far? Okay, usually when you learn a graph at an elementary level, it's just a matter of understanding the arithmetic and how it works out. Okay, we got enough information about transformations, it'll make the learning of this a little bit easier, I think. Okay, so far we've just done the up, down, the left, right, and we did a reflection. We can do stretching and shrinking also on these like we can any function. Okay, so I'm going to do this one. Now, a minute ago, we did negative 2 to the x. Remember, negative 2 to the x took the swoosh and reflected it this way. What do you suspect the negative x is going to do? It's going to reflect it this way, okay? It's changing x to opposite. So that negative right there, just think of it as x becomes opposite. That'll kind of help you understand that. Since x becomes opposite, that just means that it's moving over the y-axis, like that, okay? So what's going to happen on this then, I'm going to crunch some of these out, not all of them, but because you'll get the idea with this. So I'm going to start here, and I'm going to do 2 to the negative 0, and I'm going to do the same thing, 2 to the negative 1. I'm changing that exponent to negative. Then I'll do 2 to the negative 2, and then I'll do like 2 to the negative 1, and 2 to the negative 2. Okay, and I'll show you what happens on this, okay? So what you would have on this, when x is 0, you would have 2 to the 0. So that's still equal to 1. That doesn't change. And then you'll see this, real simple what happens. What's 2 to the negative 1? 1 over 2. Okay, so when x is 1, that becomes 1/2. Okay, then you have 2 to the negative 2, which is what? 1 over 2 squared, 1/4. Okay, so that's what's happening on this. Then if you go this way, if you do negative 2 to the negative 1, that's 2 to the first, so that gives a 2. If you do 2 to the negative 2, that's 2 to the second, so that's a 4. Okay, so notice what's happening on your tables, real simple, is basically everything is just backwards, okay? The fractions are this way, the big numbers are that way, so everything goes backwards. So if you did the same logic on this, this would just be 1 over 1,024, and then that one would be 1,024. So when we plot those points, you'll see that it reflects over the y-axis, okay? So let's plot these points then. So we have 0, 1, we have 1/2. So the graph's going to kind of go that way towards the x-axis. And then you'll have a point negative 1, 2, negative 2, 4, and so forth. So that graph goes like that. It's just flipped over the y-axis. Okay. Everybody okay with what I've done so far? Okay. We'll get to a little the stretch and shrink here in a little bit here. I'm not going to worry too much about that for now. But the other thing that we're going to look at in this section is what Eulers' number is. And in mathematics, there's probably the two most important constants are pi and e. So Eulers' number is e. We use e because Euler came up with it, and he came up with it by investigating finance, believe it or not. Okay, it's back in the 1700s, he was looking at a financial problem, knew about compound interest. We kind of had that idea established before we even knew anything about E. So let me show you what he did, and this hopefully will give you a greater appreciation for what E is anywhere and where it comes from. So I do want to show you where it comes from. So the idea is, and we'll do this kind of in a table on the next page, is what Euler did. This is the compound interest formula. A is the amount after interest. P is the amount that you start with. APR is an interest rate. N is the number of times you do interest in a year. And then the Y is the number of years. Okay? So here's what Euler did. He said, what would happen if I invest $1 as the starting principal at 100% interest for 1 year? Okay, this is how he discovered E, is just by playing with this idea. Okay, that's what mathematicians do. We just play with ideas and see where they lead us. Okay, so I'm going to have you do something on your calculator on this. To begin with, there's a couple things I want you to do. On this, we're going to write down the compound interest formula is A equals P times 1 plus, and you can do APR over N to the NY. So you want to write that compound interest formula down. That's the way our textbook does that, is like that. Now what Euler said that he was going to do is put $1 in the bank. That's going to be the principal. The APR is going to be 100%. And remember, when you take a percent, you move the decimal back 2. So when you move that decimal back 2, that just becomes 1. So you're going to plug a 1 in there, okay? And then he also said the time is 1 year. What's the variable is going to be is the N. N is going to be the number of times that you compound, okay? So I want you to put this in your calculator. And, of course, Euler did this by hand, which is, you know, back in the 1700s, was kind of a mess. But with a calculator, we can figure out this concept of E pretty quick. Now, let me show you what I want you to put in your calculator. Let's put in 1 parenthesis and then 1 plus 1 over x, okay, because that n is a variable. Just use an x and then raise that to the 1x. You can leave those 1s off, you know, a couple of those off, but that's what you're really doing, is just setting it up so that you have 1 times 1 plus 1 over x to the 1x like that. Okay, and what we're going to do is I'm going to give you a window. This window is going to be kind of weird on this. Okay, so you want to get that put in. And then the window, we're going to make the x's get real big. So let's do something like this. Let's start at 0. And then let's do something like, well, I got to get to the end of the table. So let's go all the way to like, say 50 million. 50 million. 1, 2, 3, 1, 2, 3. Okay, scale by, who cares? Let's just say a 1 like that. Yes?
You got it on the scale.
Did I do so? I see what I did. Yeah, okay. I goofed up. The scale on the x needs to be 1. Oh, come on, get up there. Okay, my calculator is stuck. Let me try this and see if it'll get back to normal here. There we go. Okay, so scale of 1. And let's see, y minimum will be 0. No, hold on, teacher. Okay, it was, I told you to do what? 50 million. Okay, 1, 2, 3, 1, 2, 3. And then the scale needs to be something like, you know, something like that. Okay, like 10 million or something like that. Okay, the y, I want you to go 0 to 3. I know why. You'll know why here in a minute. So you want to get that set up. And what we're going to do is we're going to use the calculator to fill out this table that Euler would have done by hand anyway. Okay? So we want to get that done. Okay? So there's what you put in. There's your viewing window, like that. Now what we're going to do is we're going to trace on this, okay, just to kind of get this done kind of quickly and efficiently so you don't have to worry about that. So you want to go ahead and graph. if you got your window set up, it'll just look like a straight line. It's not a straight line, it's a curve, and it's an exponential function of some sort. So what we're going to do is we're going to do this, okay? First of all, we're just going to trace these out. These are going to be the number of times you compound. So if you compound one time, if you just go trace 1, that means that the money has doubled. So after 1 year, that $1 has doubled to $2, okay? Then we're just going to trace over and over again, and I'll show you kind of what happens. So now you can put in a 4. If you were doing compounding quarterly, then the amount of money you would have is approximately this. I'm just going to round this to 2 decimals, so that's about $2.44, okay? Then I'm going to go to 12. And just kind of do this on your calculator, get it set up. That's about $2.61. So you're making more money. Okay, then we're going to go to 365. That's doing interest every day. So that would give you about $2.71. Twice a day would be, I'm going to use 730. So you're doing interest, whoops, that's not what I want to do, 730. And then that gives, I'm going to write out a few more decimals. It's 2.7164223. Now, a lot of times students think this is going to infinity. This isn't going to infinity. Your $1 is not going to become infinitely big. It's starting to level off, and you're starting to see that. If we did this hourly, there's 8,760 hours in a year, then you would end up getting this. Okay? And then this would be about 2.7181267. Well, let's go to the last one. Okay, I just want you to get the point. So if I did every second, this is how many seconds are in a year. There's 31,536,000 seconds in a year. So you get about 2.7182812. Okay? Now, what you're going to find on E, if you look on your calculator, if the calculator is fairly maybe new to some of you on this, you have E, pi is above this key, E is there. So we're just going to see what the calculator says E is. So what I'm going to do is just go to a clear screen. I can go second mode, just quit. Then I'm going to go second division symbol. That's how you get the E to come out. And then if I do that, I'm going to write down what those decimals are. That is 2.718281828. Okay, so notice this thing is accurate to like what, 5 decimals. Okay, so if you continued, what Euler found out is that that is going somewhere. That is leading to some number, and that number is E. Okay, it's a mathematical constant. That's where that number came from. Does that make sense? Okay, a lot of times students have learned something about E, but they don't have a clue what it really is. That's where it came from. That's why we call it Euler's number. He was just investigating finance, and that's the idea. Okay, well, the number E is defined to be this. Okay, that's what you put in your calculator, by the way, is you put in, really, you did 1 plus 1 over x to the x power. That's what you did on your calculator. That's what the mathematical definition of E is. It just means as n gets bigger and bigger, so the idea is n is going to infinity, then that goes to E. So that's a limit that you'll talk about in a calculus class. That's what that idea is, okay? All right, so I'm not going to worry about graphing this on the calculator because we already did this, but the horizontal asymptote is y equals E, okay? So like the problem that you just did, I want to show you this. You can do this real quick if you want to. You can take and go to zoom 6. That just changes the window. The idea on this is if you look at this, this is what's happening. As that thing goes to infinity, it's just leveling off at y equals E. That's the idea. So that's what the definition of E is it's this expression when x gets infinitely big. Does that make sense? Okay, all right. If you're going to take several calculus classes, if you go to Calc 2, then you'll start understanding a lot more about pi and how we know how to figure out all those decimals and where that comes from. You can start writing things in what are called a series. Okay, So let's see. The next thing I want to do is I'm going to do a graph of E, and we're going to kind of summarize the transformations to kind of wrap this up. Now I'm going to do with this E, again, E is about 2.71. That's a good approximation. Okay, so we're actually just going to do all this on the calculator. I'm just going to have you put this in a calculator, and we'll just fill out, let the calculator do the table of values for us and everything. So again, what you can do on this is, on a calculator, E is above the division symbol, but it's also right there. That's e to the x. So you can go second ln, and then e to the x will come out automatically. So I'm going to do that. So I'm going to go to y1 and do second ln, then you got e to the x. Okay, like that. So that's where you locate that. And then we're just going to do this in a standard window. So once you get that put in, then just go zoom 6 and standard window, and this will roughly give you what this graph's going to look like. Okay, and then we'll fill out this table here just by tracing. Okay, so let's just do, or let's look at the table. It's just as easy to look at the table on this. So once you get your graph, you can go second graph, and then look at your table of values, and I want to just get enough values on here. So, and you can kind of scroll through this. Then when you get to -10, it doesn't matter. It's just that's getting close to 0. So you can just write, it's almost 0. Okay. If you go to -2, we'll just kind of write these things out. We'll round maybe to 2 decimals. So at -2, that's about 0.14, it looks like. At -1, that's about 0.37. You have 0, 1. Okay, then at 1, you have E. Okay, so you want to write E there, and that's really about 2.71. When you get to 2, that's really e to the second, so that is about 7.39. And then when you get to e to the 10th, it's just going to get real big. Okay, so e to the 10th just ends up giving a real big number. That's probably not even all that important to write down what that is. So that's given, you know, some, I'll just write down if you want to, really big. Okay, that's good enough. So, and see, that's what happens on exponential functions anyway. So really what you would do on this graph is just plot the point 0,1. You're going to notice that shows up. That's kind of like the only number that's rational for the y value. Then 1e is just over 1 up about 2.7. And then the next one is over 2 up about 7.5. And then that looks like the exponential function 2 to the x, except it's a little steeper. Okay, so what you have here is you have the point 0,1, the point 1e, and the point 2e squared like that. Okay, so that's how that goes. So it's an exponential function. It's the same idea. Okay, so you can do the same transformations with e. And if I'm having you graph something, you'll do a little bit of the graphing with e. You can use your calculator because you get into the irrational numbers and everything. Okay? All right? And the idea is we did y equals 2 to the x. When you do e, it's really just like about 2.7 to the x. So it has the same structure to it. It's just steeper. Gets steeper faster. Okay? All right, so I think what we'll do is I want to go through just sort of the summary of transformations. And then if we have time, we'll do a couple of the exponential functions. But, you know, you always want to know how transformations work on this. So if you look at starting with this number right here, that's analogous to having a parabola and having a 2x squared. Remember, if you have x squared, that's parabola. What would the 2 do? It would multiply y by 2, making it bigger, therefore vertically stretching it. So what A is going to be is it's going to be a vertical stretch. And you want to write these down so that you know these. It's going to be a vertical stretch if A is greater than 1. Okay, that causes the y's to get bigger. Okay, it will be, and you can abbreviate some of this, it's going to be a vertical shrink if you're a fractional value if A is between 0 and 1. That's what we learned when we were doing any function. So that's what that does. Okay. Another thing that's probably good to write is you're just multiplying y values by a. If you think of it that way, that'll help you understand why it stretches and shrinks the way it does. Okay? All right? So what happens on C, okay, now that's just kind of, and it's like totally opposite of the way it is on A. That is a horizontal stretch shrink. So the way C works is like this. C is going to be a, horizontal. It's going to end up being a horizontal stretch, and it's the same stuff. It'll be a horizontal stretch if A is greater than 1. So these things are opposites of each other, okay, like that. Okay, and then this is going to be a vertical, no, not vertical, horizontal. Okay, when we do this transformation, we're doing horizontal. So that will be a horizontal shrink if 0 is less than A is less than 1. So those things are just backwards. They're just totally backwards of what they are on the vertical. Okay. We learned this. We looked at this. What does the D do? That's inside the exponent. So what does that do? That's left-right stuff. Okay. So what this is D is, we would just say, usually on this you just say, we can just say left-right. That's good enough. Okay, so if it's a plus D, that goes to the left. If it's a minus D, it goes to the right. Okay, same thing. All functions always work the same way. Okay, and then the other thing is the E. The E is outside, so what does that do? That's up, down. Okay, so that'd be just like where you have a parabola where you go plus 3, it moves everything up 3. So E is just up, down. If it's plus, it's up. If it's minus, it's down. So it goes like that, okay? And then the other thing is, what would happen if A was negative? We did a problem like that. What happens if A is negative? What does that do to the graph? Flips it this way, flips it over the x-axis. So this would be reflect over x. You want to make sure you know which axis. So let's reflect over x. And then negative C, that would be working on the x, that would be reflect over y. Okay, like that. So that's how that basically goes. Those are the way that it works on any function, but an exponential, that's where the numbers are. Okay? All right? Let's finish up by just doing some of these. We probably won't have time to do all these, but what you ultimately want to know is look at a function and know what these numbers do. Now this one we're just doing e to the x. So what does the 2 do? It's outside adding. What does that tell you? Up 2. Outside. Anytime it's outside, it's affecting y values. Okay, how about adding negative 4 outside of the exponent? Down 4. Good. Okay. Okay, so again, that's just that's outside of the exponent. Okay. And how about the next one? What's that going to be?
Left 3.
Left 3. It's inside, so that's going to be left 3. And then the last one is going to be
Right 2.
Right 2. Okay, that's how that goes. Okay. Then we get into the reflections. How does number 5 reflect? Which way? Over x or y? Reflect over x. Okay, the next one would be reflect over y. It depends on where that negative is. Okay, how about number 7? You're multiplying y by 2. So what is that going to do? Stretch vertically. So we'll say vertical stretch. And how about the next one? Multiply the y by a fraction, y gets smaller, so what does it do to the graph? Shrink. Okay, good. So that's a vertical shrink. And then the last one has several transformations. Let's just write this one down, then we'll finish the last page up next time. So basically, the 2 does right 2. The plus 7 takes you up 7. The 1/4 is a vertical shrink. Okay, and then the negative reflects over x-axis, like that, okay? So once you get these down, they're the same again for every function you ever learn. So it's a little bit easier when you get a little bit to different kinds of functions. It'll work the same thing on logarithmic functions, okay? All right, so we'll finish this up next time and then next week we'll get into logarithms and kind of wrap everything up for the college algebra part of the class. It looks like your test 2 is going to be 2 weeks from today. Okay, so I'll start kind of over the weekend putting together some